Okay. This really goes right along with the things that we were learning like throughout chapter 4 so far. The big thing we looked at was how we can use the derivative to find out more information about our function. In Rolle's theorem and mean value theorem, still same thing. We're just diving into derivatives. So the next group of sections that I will teach you, I think it's 4.6, 4.7, 4.8. And then 3.8, 3.9. I think that's what it is. I can't remember exactly. Maybe it's 4.7, 4.8, 4.9, 3.8, 3.9. I think that's what it is. Those 5 sections I'm going to group together and then assess you on that to round out chapter 3/4. And then we'll move on to something a little different after that. But okay, so 2 main theorems in this section. Rolle's theorem is fairly important, but mean value theorem is going to be a theorem that kind of follows us through the rest of the course. So I put a star on that in our notes. That one's very important. Rolle's theorem is a good note card theorem as well too. However, justifying things using mean value theorem will be on the AP exam, so it is remarkably important. Okay. All right. So first of all, Rolle's theorem. I can't remember if it's Michael or Michel. I can't remember how you pronounce this mathematician's first name. But here's the theorem says this. If you have a continuous function f on a closed interval that's differentiable on an open interval, and if f of a equals 0 and f of b of that interval equals 0, then there has to be some number c in between a and b such that f prime of c is equal to 0. Meaning, if I have a function that's continuous on a closed interval, differentiable on an open, and the outputs either equal 0, which is what your textbook cites, or if they equal each other, then there has to be a turning point at some point in the function such that you have a relative min or a relative max. Okay? You can have more than one. If I drew something that looks like this, very thick line. So if I had something that looked something more like this, let's say A is here and B is here, then obviously I've got 2 values such that the slope of my tangent line is going to be equal to 0. So I would have 2 C values that give me that value. So at least one, could be more than one. Okay. However, if one of those caveats are not met, so if it's not differentiable or if it's not continuous, then Rolle's theorem does not apply, such as this next example here, which shows, okay, I've got a function that is continuous on this closed interval. However, it's not differentiable because what do we have at this value of c? A sharp term. So that would make it not differentiable. So because of that, Rolle's theorem would not apply. Okay. All right, so given y equals sine of x on 0 to 2 pi, verify if Rolle's theorem, the hypotheses for Rolle's theorem are satisfied. And if so, find all the c values guaranteed by Rolle's theorem. Okay, so before we get into taking the derivative, we got to make sure that the 3 conditions for Rolle's theorem are met. Okay, first one is my function has to be continuous. So y equals sine of x. Is that continuous on that interval? It is. Cool. So f of x, or I should say y rather, so use proper notation. So y is continuous on the closed interval, 0 to 2 pi. Okay. What about differentiable? Does my derivative take a value everywhere on that interval? It does. Sometimes it's a little less obvious. Sometimes you actually have to take the derivative before you can actually answer that question. Hi.
Hello.
All right, it's also differentiable on 0 to 2 pi. So then the other thing we need to check is to make sure that my endpoints have an output of 0 as well too, okay? All right, so if I think about this like a function, y of 0 would be sine of 0. What is sine of 0? 0. And then also y of 2 pi. So if I plug 2 pi in, I would get sine of 2 pi, which also gives me an output of 0. Cool. So then in that case, all 3 of my conditions are met, so I can use Rolle's theorem to find those C values that are guaranteed by that theorem. Okay, so what that looks like is now I need to take my derivative. So y prime is equal to cosine of x. And then we would set that equal to 0 and find our values that are guaranteed. Okay. All right, so think about unit circle. Boom. Where is cosine equal to 0? That happens how many times in that interval? Twice. It's pi over 2 and at 3 pi over 2. Okay, so I'd get x equals pi over 2 and 3 pi over 2. Sometimes what you might see is since we call this letter c, when it comes time to taking the derivative and setting it equal to 0, you might actually see me write, instead of cosine of x, I might write cosine of c equals 0, and then c equals pi over 2 and 3 pi over 2. It's just other notation that I might use. Okay? All right. Cool. Let's say we're given y equals x squared minus 3x minus 3 over x plus 2 on the interval from -1 to 3. Verify the hypothesis. If the hypotheses of Rolle's theorem are satisfied, and if so, find all C value guaranteed by Rolle's theorem. All right, first of all, is our function continuous? Yeah, so it's not continuous at what value? -2. However, it needs to be continuous on our closed interval. And since -2 is not a part of that interval, then I can say that my function is continuous on that interval. So I can say that y is continuous on the interval from -1 to 3, because x equals -2 is not an element of -1 to 3. So -2 would be our issue, not on that interval though, so we're cool. All right. Is it differentiable? What would be the value that would make it not differentiable? Again, -2, right? Think about like if I took the when I take the derivative of this, because I'm going to have to, what's it going to require me to use? Okay, so low d high minus high d low over low squared. So I would have over quantity x plus 2 squared in the denominator, which again, -2 makes that discontinuous. So it would make my y function not differentiable, but not in my interval, so I'm cool. So y is differentiable on my open interval from -1 to 3. All right, so then the other thing I need to do is I need to test my endpoints of my interval and make sure that they both have an output of 0, okay? All right, so y of -1 equals -1 squared minus 3 times -1 minus 3 over -1 plus 2. All right, so up top I would have 1 and then minus 3 times -1, which would be 4 minus 3 gives me 1 over -1 plus 2 is going to give me 1, so that's going to give me 1. All right, so that's not 0, but here's something I do want to check. Let's check to see what 3 is going to be. So if I plug in 3, not -3. So 3 squared minus 3 times 3 minus 3. I know what I did. I made it, okay, here's what I did. I wrote this problem wrong. It should be -2x, not -3x in the beginning. Sorry, that's not going to change it too much, but it is going to change our outputs for the first one. So, sorry, this should be -2x. That's my bad. I typed it in wrong. Okay, well, if that's the case, and it's actually -2x, then that changes my output, right? Okay, so I'd have -1 squared minus 2 times -1, so it'd be 1 plus 1, which is 3, and then minus 3, which would give me 0. So 0 over 0. Sorry, not 0 over 0, 0 over 1, which is 0. Okay, then when I plug in 3, I should get the same output. So 3 squared is 9, minus 6 is 3, minus 3 is going to give me 0 up top. And then my denominator would be 3 plus 2. Doesn't really matter. 5 gives me an output of 0. Okay? All right. So then in that case, let's see. Can I change this real quick? That way I don't forget to do it. Okay. I apologize. Okay, cool. So it's continuous, it's differentiable, my endpoints agree. So now what I want to do is I want to take my derivative, set it equal to 0, and then find my values, okay? All right, so then I'm going to do that down here. And I got to use quotient rule, so y prime equals low, which is x plus 2 times d high, which would be 2x minus 6. No, sorry, 2x minus 2. Okay, so low d high. Minus high, which is x squared minus 2x minus 3. D low, which would just be 1 over low squared. Okay, so then now what I want to do is I want to simplify that and see what we get. So 2x squared minus 2x plus 4x minus 4, and then minus x squared plus 2x plus 3. All right, so I get x squared, and then plus 4x, and then negative 4 plus 3 is minus 1 over x plus 2 quantity squared. Uh-oh. What's that mean? Quadratic formula, because my next objective is to set it equal to 0 and then find what my roots are. So I do indeed need to use quadratic formula. So negative 4 plus or minus square root of b squared, so 4 squared, minus 4 times 1 times negative 1, all over 2 times 1. All right, I don't think it's going to simplify into anything nice for us because it does not factor. All right, so 16 plus 4 is going to give us 20. That's not bad, we can deal with that. Over 2. What's wrong? Okay, so how can I break down 20? 4 times 5, so 2 squared of 5. And then I can divide everything by 2. So then that would give me negative 2 plus or minus square root of 5. All right, so those are my 2 roots. I need to find, do both of them follow my interval? Does just one of them follow my interval? Square root of 5 is going to give me what? It's like 2.23 or something. I'm not really sure what it is. Something like that. Okay, so if I do negative 2 plus 2.23, that would fall inside my interval. But if I do negative 2 minus square root of 5, that would be negative 2 minus 2.23. Will that be in my interval? No, it will not. So the only one I care about is this value right here. All right. Okay. All right. Let's talk about this one real quick. All right. F of x equals absolute value of x minus 1 on the interval from negative 1 to 1. Okay, so in your mind, think about what the graph of absolute value of x minus 1 looks like. Is it continuous on negative 1 to 1? It sure is. Is it differentiable? No. Why not?
Because there's a sharp turn.
It's a sharp turn, right? So think about what this process would look like if we were to fully flesh that out, right? We can say it's continuous because it's a composition of continuous functions, so we're cool there. However, to check to see if it was differentiable, I would have to set it up as a piecewise function and then take the derivative of that piecewise function, right? Your derivative for each one of your cases, one of them would be 1, and then since I have absolute value of x, I'd have to hit it with a negative, so the other derivative would be -1, and we would see that those two clearly don't equal each other when x equals 0. In fact, there's nowhere to actually set that equal to 0 because my piecewise function is just 1 and -1. Nothing's going to make that 1 anyway. So we would say f of x is not differentiable when x equals 0. Rolle's theorem does not apply. All right, so that's Rolle's theorem. Let's talk mean value theorem. More applicable, less specific, will come up much more often. I put a star there because it's important. Mean value theorem says this. The preamble is very similar. F still has to be a continuous function on a closed interval. Also has to be a differentiable function on an open interval. So same two first conditions apply. Then it goes right into the upshot, which says there's at least one point C in that open interval such that f prime of C equals f of B minus f of A over B minus A. What is this? This is what? Yeah, slope of a secant line, okay? Now, this is slope of a secant line on the right side. What is this on the left side? Slope of a secant line gives us average rate of change, yeah? What is f prime of C? What type of rate of change is that? Instantaneous rate of change. So it basically says this. If your function is continuous on a closed interval, differentiable on an open, then there has to be some value C such that the instantaneous rate of change is equal to the average rate of change on that interval, okay? So that upshot is that's the important part of the theorem itself, okay? Using the theorem looks like this. Make sure it's continuous on a closed, make sure it's differentiable on an open, and then compute what your average rate of change is, or your slope between your endpoints, and then you set your derivative equal to that value and you solve for C, okay? So that's what it looks like, all right? So it implies, again, that your average rate of change is equal to your instantaneous rate of change. It essentially says the same thing that Rolle's theorem says. It just tilts it a little bit, right? Rolle's theorem would say that these two endpoints would have to agree, or they would have to have an output of 0, and then your average rate of change has to be 0 at some point. This just says, all right, well, if we tilt that a little bit, and this is your average rate of change, there has to be some value on that interval such that its average rate of change its instantaneous rate of change is equal to the average rate of change between your endpoints, okay? All right, so let's look at that. All right, so given y equals x cubed over 4 plus 1 on the interval from 0 to 2, verify the hypotheses of mean value theorem are satisfied, and if so, find all C guaranteed by the mean value theorem. All right. Is it continuous? Yeah, it is. So y is continuous. I was looking for any denominators or square roots or anything like that, and none of that is there. So it's continuous on our closed interval from 0 to 2. Polynomials are continuous everywhere. Likewise, they are differentiable everywhere as well too, right? So y is differentiable on our closed interval from A to B. That's all I have to check. That's it. Just those two things, okay? I don't have to do anything with the endpoints or anything like that, okay? So then now what I need to do is I need to find my C values that are guaranteed, okay? And I'm going to go about that by computing my average rate of change and then setting my derivative equal to my average rate of change and then solving for C, okay? All right, so let's find the slope of my secant line. So in order to do that, I need to know what my outputs are at 2 and at 0, and then I'm going to subtract 2 minus 0 in my denominator. All right, I think we can do this mostly in our heads. So if I plug in 2, 2 cubed is 8. 8 divided by 4 is going to give me 2. 2 plus 1 is going to give me 3. So my output for 2 is going to be 3. What is going to be my output for 0? Hooray. Over 2. So 2 over 2 is going to give me a slope of 1, which means I need to take my derivative and set it equal to 1, and then find my c value. Okay? All right, so y prime is equal to, all right, what's that derivative look like? Good. So 3/4 x squared, or 3x squared over 4, however you want to say it, doesn't matter. But now I need to set that equal to 1 and then solve for what that value is, okay? Multiply both sides by 4/3, so x squared equals 4 over 3, and then I would take the square root, x equals plus or minus square root of 4/3, or plus or minus 2 over square root of 3, or get crazy and say plus or minus 2 square root of 3 over 3, if we rationalize it. Do both of those follow my interval? No, they don't. Does one of them follow my interval? I would assume so. I mean, if you take 4 over 3 back to our initial value, 4 over 3 is going to give you, 1.3 repeating. Square root of that is going to be a number that's in between 0 and 1, and that's in our interval. So because of that, we would say that we want x equals 2 square root of 3 over 3. It's going to be our value. Or instead of saying x, would be more proper to say c. As long as you pinpoint that value, that's what I care about, though. Okay? All right. How we feel? We doing okay? Okay. All right. Yeah, I got a couple of good ones in here still, and I still have a little bit of time, so I'm gonna keep trucking. All right, given y equals 2x to the 1/3 on the interval from -1 to 2, verify the hypothesis of the mean value theorem is satisfied, and find LC guaranteed by the mean value theorem. Okay. Is y continuous on that closed interval? Do I have any breaks, holes, or gaps, fractions, anything like that I need to worry about? The only fraction shows up is with an exponent, and so far that's fine. So y is continuous on the interval from -1 to 2. Okay? All right. Is y differentiable? No. Why not, Ashley? Good. There's a vertical tangent line at 0. If you didn't spot it straight away, then at some point you would get to the part where you would want to take the derivative. And let's look at what that derivative is, just in case you didn't spot it right away. You'd have 2/3 x to the -2/3, also known as 2 over 3, and then x to the 2/3 in the denominator. And then when we write our derivative that way, we can see, oh, I now have a denominator and an instance for it to be discontinuous. So since my derivative is discontinuous at 0, that means it is not differentiable. So y is not differentiable on my open interval from -1 to 2. Okay. Not Rolle's theorem, but mean value theorem does not apply. Ashley correctly stated that it's going to be a vertical tangent line. So it's going to happen at 0. So because of that, mean value theorem will not work out. Okay. All right. Let's do some trig. F of x equals tangent of x on the interval from -π/4 to π/4. Verify the same instructions as always, but we're working with mean value theorem here. Okay. All right. Tangent's a sneaky fraction. We should think about it like sine of x over cosine of x. Obviously has some discontinuities. Do any of them happen on our interval? No, we got to think a little harder about that. She's right, though. Where do my discontinuities happen for cosine? Or where do the zeros happen, I should say? not at 0. Pi over 2 and 3 pi over 2, right? So those happen here, but my interval is only from negative pi over 4 to pi over 4, so I'm good. I have no discontinuities on that interval, okay? So because of that, that means f of x is continuous on the closed interval from negative pi over 4 to pi over 4. All right, is it differentiable? Let's do a little foreshadowing. What is the derivative of tangent? Secant squared, which gives us 1 over cosine squared, which would have discontinuities as a function, the same place where tangent has discontinuities, right? So pi over 2, negative pi over 2. Even though cosine is squared, those instances would still be discontinuous, okay? So because of that, f of x is differentiable. Oh my gosh, look at you guys. Now we get to do the thing. All right, so I've already taken my derivative. Now I need to find what my average rate of change is so that I can set my derivative equal to that average rate of change and find the values that make that magic happen. All right, so I would want f of pi over 4 minus f of negative pi over 4 over pi over 4 minus negative pi over 4. Something tells me I'm not going to get a nice value here to set it equal to. We'll do our best, though. All right, pi over 4. What is tangent of pi over 4? Oh my gosh, thank goodness. That's a nice value. All right, what about negative pi over 4? Okay. So then I would have pi over 4 minus negative pi over 4. What's that turn into? We have pi over 4 plus pi over 4, pi over 2. Which gives me 2 over pi over 2, which is 4 over pi. Well, that's great. That's not a value on our unit circle, is it? Not one we're familiar with. It's on there, but, you know. Okay, so then in that case, I need to take my derivative, secant squared, and I need to set it equal to 4 over pi. Okay. All right, well, we've got to solve it. Take the square root. Secant x equals plus or minus square root of 4 over pi. Simplify this a little bit. Secant x equals 2 over square root of pi. Plus or minus is still there. Well, we can make a cosine and then flip our fraction, right? 1 over cosine equals plus or minus 2 over square root of pi. And then take the reciprocal. Cosine of x equals plus or minus square root of pi over 2. Is there any way that I can find these values without a calculator? Unfortunately not. So I'd have to use a calculator in order to figure out what our values are. Okay, so I'd want to figure out where does cosine equal plus or minus square root of pi over 2. How would I go about doing this in my calculator? What would I have to use? Inverse cosine, good. Yep, so use inverse cosine and we can find those values, right? All right, cosine inverse of positive square root of pi over 2. And then I need to do cosine inverse of negative square root of pi over 2. All right. There's got to be clear all there is. Okay. Am I in radians? I am. Okay, cool. Function. Cosine inverse. All right. Square root of pi. And then divided by. Nope. Don't do that. There we go. Okay. All right. So there's one value. 0.48 1, 7. And then let's sneak a negative in there. And I would get that at x value is 2.66. We're just going to round it. However, is that value in our interval? No. Pi over 4 is less than 1, so that's no bueno. So that's our value. Okay. What time do I have you guys till? 50. Roger. All right. Let's look at this last one. All right. 2 cyclists begin a race at 8 a.m. They've both finished the race 2 hours and 15 minutes later. Prove that at some point during the race, the cyclists are traveling at the same velocity. All right. I'm going to give us a ton here. They both begin a race at 8 a.m. and then they both finish the race at the same time. So at some point, we have to prove that they're traveling the same velocity. Now, can we assume that they're just like riding side by side the entire time? No. They're probably changing velocity throughout the race, right? Independent from each other, right? So here's what we can assume. We know that they start at the same place, right? And then they end at the same place at the same time, okay? We can also assume this is a continuous function, right? And is differentiable. They'll have a rate of change at every point in between when they start at 8 a.m. and then they finish at 10:15 in the morning. So we can assume those things. We know it's differentiable. We know it's going to be continuous. They're just going to be traveling. Their position has a value at each one of those points. Okay. Rather than think about because we have to try to think about how we can apply one of our theorems to this situation here. Okay. Now, does this fit into Rolle's theorem? We know that they have, we know they start at the same time and then they finish at the same time. So it's kind of like our endpoints agreeing with each other, right? They start and finish at the same time. So in order to force this to fit into the Rolle's theorem that I gave you guys, you could also think about it this way. So if you think about cyclist 1 having their position being, let's say, f of t, and then cyclist 2 having their position be g of t. What we could do is we could think about the distance between the two, h of t, being f of t minus g of t. So if we define a separate function as h of t, and think about it like distance, okay? Now, let's say we've got our interval. What would our interval be? Let's say 0 to, and then if we did this in hours or whatever, it would be 2 1/4 hour, right? So then that would be 9/4 if we're doing it in terms of hours, okay? So what would h of 0 be? What's the distance between them at the starting line? 0. What is the distance between them at the finish line? So then which theorem is going to apply? Rolle's theorem applies. Okay, so because h of t is continuous on our closed interval from 0 to 9/4, and h of t is differentiable because it's the difference of two differentiable functions on a closed, or an open interval rather, of 0 to 9/4, then by Rolle's theorem, there must be a value c, an element of our interval from 0 to 9/4, such that h prime of t, or I should say h prime of c rather, sorry, h prime of c equals 0. What does h prime of t represent? That'd be the difference in their velocities, right? Because if, f of t is their position, the derivative of f of t is f prime of t, which is the velocity of cyclist 1. And then same thing with g, same story there. G prime of t would be this velocity of cyclist 2. So the difference in their velocities would be 0, which makes them traveling the same rate at some point in that interval. Okay? All right. Your homework is as follows. Do 1 through 3, 5 through 16, 19, and 21. 1 through 16 are problems related to showing that Rolle's and mean value theorem apply. 19 and 21 would be more of like an application type of problem. Okay? All right. Grab a calculator. Spread yourselves around. I'll give you a little bit of time to finish up your tests. If you need more time, if you don't need more time, totally fine.